Hello and welcome back to the Science of Concrete Materials class. This is lecture number 31 of the class. So far we have covered these topics shown here on this slide. All these topics shown grayed out. We covered. The last topic we talked about was the proportioning of the concrete mixtures. Today we will start on the new module of the class, which is the response of concrete to stresses. Okay, so this is like an introduction before we actually discuss the hardened concrete properties such as strength and deformations. We need to understand how the concrete responds to applied loads, or otherwise how it responds to stresses. Okay, so we will be looking at these topics: the non-linear behavior of the concrete, the response of a composite material, the elastic moduli, the different types of the elastic moduli, how we determine the elastic modulus. Basically, there are models proposed how to determine it. There is also a practical determination of how to determine the elastic modulus, Poisson's ratio and how it relates to the elastic modulus, the factors that affect the modulus of elasticity, tensile strength, compressive strength, and the factors that affect strength as well. Okay. Before that, let us really refresh on the stress-strain relationship in general. So if we look at the curve shown here, we see several terms defined: stress, strain, modulus of elasticity, proportional limit, Hooke's law. We see here the ultimate strength and the fracture point, the yield point. This is basically a stress strain curve for a low carbon steel bar subject to tension, and you see how it goes through this area. The elongation follows a straight line up to a certain point. Then we have the yield point after the element has yielded. Then after that we have the strain hardening region, basically the rearrangement of the atoms as well. And we reach the ultimate strength. After that, the material will fail or will fracture rather. Okay, so this is just a general description of the stress strain curve for this element, which is the low carbon steel bar in tension. Okay, if we look at the curve and we see these different items or terms I just explained, the Young's modulus of elasticity is basically the elastic modulus of for tensile and compressive stress in the linear elasticity regime, as you can see here, okay, of a uniaxial deformation, and it's usually assessed by tensile tests, typically for ductile materials mostly. The Young's modulus is named after that 19th century British scientist Thomas Young, so that you know. So most polycrystalline materials have within their elastic range, an almost constant relationship between stress and strain. Okay. In 1678, an English scientist named Robert Hooke ran experiments that provided data that showed that in the elastic range of a material, strain is proportional to stress, as you can see here. Okay. So in case of tensional stress of a uniform bar, as you can see on this curve, the Hooke's law describes the behavior of a bar in the elastic region And again, as I said, in this area. In this region, the elongation of the bar is directly proportional to the tensile force and inversely proportional to the cross-sectional area and the modulus of elasticity. Okay? So up to a limiting stress, as we can see here, this is the proportional limit. A body will be able to recover its dimensions on removal of the load. Okay, if we remove the load here, it will recover back to, its dimensions. The applied stresses, what happened, cause the atoms in a crystal to move from their equilibrium position. All the atoms are displaced at the same amount and still maintain their relative geometry. Okay, so when the stress is removed, all the atoms return to their original positions and no permanent deformation occurs, as happens here. If the load is removed up to this point, if the load is removed, all atoms return back to their original position and there will be no permanent deformation. That's what happened actually in this elasticity region. Any material that follows this behavior. So according to Hooke's law, the stress is proportional to the strain, again, in the elastic region, right here. And the slope is Young's modulus, the slope of this line. So Young's modulus is equal to the longitudinal stress divided by the strain, okay? As, which follows this equation. Stress equals Young's modulus times strain. Sigma is the stress in whatever units you're using, Pascal, for example. Epsilon is the strain, which is dimensionless value, basically, which is the change in length, per original length. And E is the modulus of elasticity in the same unit, Pascal, or whatever units you are using. Okay, so one thing we need to remember, concrete does not behave in this manner. Okay, this is basically for ductile materials like iron, for example, or steel. Okay. Okay, so what are the mechanical properties of a material that would be of interest actually from the viewpoint of an engineer? Basically, as we said, we have the elasticity and stiffness, recoverable stress versus strain, ductility, which is the non-recoverable stress versus strain, as we'll define here, strength, other terms, like hardness, brittleness, toughness, for example, and fatigue. Okay, so these are basically the terminology, the mechanical properties of a material that an engineer will be interested in. Okay, so if we look, at the behavior of materials. So okay, when a load is applied to a material, and as we know, it may deform the material. Actually, it will, but depending on the load and the material. What do the force, extension, or the stress strain curves look like? Okay, and what is the modulus of elasticity of ceramic, metal, polymer? We saw for a metal what it is for a ductile material, as we have seen from here. Okay, but how it is determined, for example, for ceramic, a material like concrete, or for a polymer. Look at this curve, for example, here, which shows you the behavior of the three different major materials I mentioned here. For example, look at the ceramic. Ceramic is a brittle material. It shows no ductility. So basically the material will be stressed and it will fail suddenly. Okay, this is the metal. The metal is ductile. Basically, it will show this linear stress-strain relationship in this region. And after that, it will follow this curve right here until failure. This is the behavior of a ductile material. This is a brittle material like ceramic, concrete. On the other hand, look at the, for example, an elastomer, which is a polymer, how they behave. Look at the behavior. It's very strange. Stress strain curve. It's very, it deforms, easily, but at some point it will show some hardening behavior, which is probably due to the rearrangement of the particles or something like this. And just that the point of this curve is actually really to show you the different behavior under load for 3 different materials: ceramic, metal, polymers. Okay, so the elasticity and stiffness, what are they? The elastic deformation is the deformation produced in a material which is fully recovered when the stress causing it is removed, okay, as we saw in the previous slide. Stiffness is a qualitative measure of the elastic deformation produced in a material. So a stiff material has a high modulus of elasticity versus a soft material which has a low modulus of elasticity. Okay, the modulus of elasticity, or Young's modulus, which is basically the slope of the stress strain curve during the elastic deformation, as we have seen here. Okay, what is ductility? Ductility is the ability of a material to stretch or bend permanently without breaking. As we can see here, for example, this is a ductile behavior, which is that steel we talked about earlier. Okay, after yield, basically it's still, it has the ability to bend and deform, permanently without breaking up to a certain point. The brittle material like the concrete or the ceramic, it does not. It actually breaks suddenly under load. It does not have the ability to basically stretch or bend permanently before breaking, without breaking. Okay, so with all that in mind, let's talk about concrete. Concrete is really a complex, heterogeneous material, and its response to stresses, depends on the response of the individual components that makes up the concrete, and also on the interaction between these individual components. Okay, so the complexity of the interaction is really illustrated in the figure I'm going to show here in a minute. Okay, so the figure, shows typical compressive stress strain curves for concrete and its mortar, cement paste, and the coarse aggregate constituents, as you can see. Okay, so the coarse aggregate is a linear brittle material with a strength significantly above that of the concrete, as you can see here. Okay, the cement paste has a lower modulus of elasticity but a higher compressive strength than does either the mortar or the concrete. All right, so the addition of fine aggregate to cement, to cement paste to obtain mortar results in an increase in the modulus of elasticity but a reduction in the strength, as you can see. Okay, so this is the cement paste, this is the mortar. We increased the modulus of elasticity, but the strength was decreased. Okay, so the addition of the coarse aggregate, furthermore, the addition of the coarse aggregate to mortar to obtain concrete, all right, in the case shown here, has little effect on the modulus of elasticity, as you can see. Okay, but results in an additional reduction in the strength. If you see the compressive strength, that is, by the way, this is the concrete and this is the mortar. Okay, modulus of elasticity did not change much, but the strength, the compressive strength, was reduced. All right, so overall, the behavior of the concrete is similar to that of its mortar constituent, while the behavior of both the mortar and the concrete is significantly different from the behavior of either the cement paste or the aggregate, as you can see. All right, So the stress strain, curves shown here emphasize that concrete is a composite material, that is a combination, of two or more distinct materials with a definite interface separating the components. A multi-phase material is expected to have different properties from the original components making it up, and clearly concrete qualifies as such. Okay, so for concrete, at the macroscopic level, concrete consists of coarse aggregate embedded in a matrix of mortar. On a somewhat finer scale, the mortar consists of particles of sand embedded in the matrix of hydrated cement paste. On even finer scale, on the microscopic scale, the hydrated cement pastes consist of the amorphous calcium silicate hydrate we talked about before, and the crystalline components like the calcium hydroxide, which containing an extensive network of capillary pores that may be dry or filled with water, plus grains of unhydrated cement and grains of submicroscopic calcium sulfur-aluminate hydrate crystals, as you recall. Okay, so still on a finer submicroscopic scale, the calcium silicate hydrate is a mixture of poorly crystalline particles of a variety of shapes and chemical compositions, and more or less continuous system of gel pores, which also may be dry or partially completely filled with water, as we explained before. The aggregates themselves are also generally composite materials per se, consisting of mixture of different minerals with a well-defined porosity. If you remember, we mentioned something like this when we talked about aggregates. Okay, so if we look at the what we just talked about, this is just a representation of the change from the macro scale to the sub-micro scale of the concrete. This is the concrete structure, the reinforced concrete structure we see, like a concrete beam, column. That's what you see, the element as a whole. This is on the scale of larger than 10 to the minus 1 meter, 0.1 meter. We have a finer scale, which is the mesoscale of concrete, which is 10 to the minus 2 to 10 to the minus 1, basically, which is mortar plus aggregate particles and interfacial transition zone. That's what you can see on a sliced polished section. We have the finer scale than that, which is the mesoscale for the mortar, 10 to the minus 3, 10 to the minus 2 meters. Basically cement paste plus sand particles and interfacial transition zone between them. At the micro scale, we will see the cement paste, which is on the order of 10 to the minus 4 of a meter. What you will see, of course, this is a microscopic scale. Basically what you will see, the capillary pores plus the calcium silicate hydrate matrix, calcium hydroxide probably, and some clinker phases. This is the sub-micro scale, basically 10 to the minus 7 meter. Basically what you see, calcium silicate hydrate matrix and the capillary pores, as you can see here, maybe the calcium sulfur-aluminate hydrate phases, which we talked about it during the hydration lectures. Okay, so this is just to give you really an appreciation of the scale between the macro scale, what you see with the naked eye, to what you see here in the what you will see at the nanoscale. Okay, also, as we have mentioned before, remember this, the structure of the cement paste constituent at the boundary with the aggregate particles differs from that of the bulk cement paste, resulting in the formation of the interfacial transition zone, or the ITZ. You remember that. This zone, the ITZ, plays a role in the stiffness, strength, and permeability of cementitious materials containing aggregates due to its generally low density and decreased strength compared to that provided by the bulk cement paste. Okay, so this is often referred to as the weak link in concrete. I will elaborate on this ITZ a bit later here in this presentation. So, as I mentioned in this module, we will look at the behavior of concrete under stress from both the theoretical and practical aspects of that response. Emphasis is placed on material behavior under what is often, referred to as static loading, which is loading rates that are typically obtained under standardized test conditions. So remember, the testing condition or the testing routine makes a difference. So even under such conditions, though, however, the response of concrete is sensitive to the nature of the tests, including that, the degree of restraint, the moisture content, and the rate of loading, since there is virtually no aspect of the mechanical behavior of concrete that is not affected by these factors. So remember the sensitivity to testing, the rate of loading, the testing regime we are using, all make a difference. Okay. All right. So traditionally, concrete has been modeled as a two-phase composite material consisting of inert aggregate particles with wide size distribution embedded in a uniform matrix of hydrated cement paste. For normal aggregates and concretes, it is then assumed that the mechanical and the transport, basically diffusion and permeability properties, depend primarily on the water-cement ratio. For normal engineering purposes, such model provides a sufficient degree of accuracy. However, it represents a considerable oversimplification of the true structure of concrete. It is well known that there is a thin zone surrounding the aggregate particles in which the structure of the cement paste is quite different from that of the bulk paste, further away from the physical interface, in terms of morphology, composition, and density. Okay. So this zone, typically about 20 to 40 micron thick, which is, as we said, referred to as the interfacial transition zone, or ITZ. As discussed previously during the study of the hydrated cement paste, structure, the structure of the ITZ is different from that of the bulk paste in the following respects. There is less unhydrated cement in this zone. There is a higher porosity and, hence lower density. The pores are generally larger than those found in the bulk paste. There is less calcium silicate hydrate. There are large oriented crystals of calcium hydroxide. There is generally a greater concentration of ettringite. This basically what we can say, these are basically some of the general properties of the ITZ. As you can see here, this is just a schematic. This is the aggregate particle, this is the bulk paste, and this is the area referred to as the transition zone. It's represented to be, less dense than that of the bulk paste. Okay. So what are the, what we see are the effect of the ITZ on the mechanical properties. What are they? Currently, there are no standard test methods by which, strength of the ITZ, or more importantly, the bond strength between the aggregate particles and the ITZ can be measured. There is no such thing. So the bond strength, depends on the surface characteristics or the roughness of the aggregate particles, on the degree of bleeding, the chemical bonding in some cases, and on the particular specimen preparation techniques, which is basically not easy to measure. So it is not possible to reconcile the results of the various investigations that have been reported because they're all over the place. All right. However, it is generally found that as the paste aggregate bond strength increases, the concrete strength also increases. Okay, whether in tension, flexure, or even in compression. All right. So these increases range from about 5 to 40%, with improvements in tensile strength actually being higher than those in compressive strength. We're talking about comparatively. In ordinary concretes, the ITZ has less crack resistance than either the aggregate or the hydrated cement paste, and so fracture occurs preferentially in the ITZ, which then constitutes, as we said, the weak link in the concrete. However, though, to produce truly high strength concretes, in the range of above 70 MPa or 10,000 psi, that is, it is necessary to increase the strength, both of the paste matrix and the paste aggregate bond. That is very important in order to produce this high strength concrete. But unfortunately, reducing the water cement ratio has much greater effect on the matrix strength than it does on the strength of the paste aggregate bond. So the focus has been on improving the strength of the ITZ itself, since fracture usually occurs not right at the physical interface, but about 10 to 20 microns into the ITZ, away from the aggregate face. Okay. So the most effective way of improving the ITZ is the addition of 10 to 15% of silica fume by weight of cement. Remember, the silica fume, if you want to refer back to the mineral admixtures lectures, is very good in this regard, and for several reasons. First, it eliminates many of the large pores in the ITZ, making its structure more homogeneous. It eliminates the growth of the calcium hydroxide, or transforms the calcium hydroxide to calcium silicate hydrate, through the pozzolanic reaction. Also, it has that filler effect that modifies the rheological properties of the fresh concrete in such a way to reduce internal bleeding, so by that it enhances the paste aggregate bond. Currently, though, the use of silica fume is the most effective way of densifying the ITZ. However, other techniques are being examined, such as using chemical reagents, for example, surfactants or water glass in the concrete mix. Such treatments may in the end, provide more economical means, achieving better bonding. And for ordinary concretes, improvements in the ITZ or in the bond strength otherwise are unlikely to lead to major changes in concrete behavior. So you have to keep that in mind, the cost-benefit analysis. The modest increase in the strength, attributable to better paste aggregate bonding will, are largely offset by the increase in brittleness of the resultant materials. So you gain something, you give up something. However, for high performance systems, such as, high strength concretes above 100 MPa, concretes, high strength fiber reinforced systems, or systems containing special aggregates such as, graded stainless steel aggregate, high bond strengths resulting, from the improvement in the properties of the ITZ, appear to be, more important if the full potential of these special materials is attained. Okay, so when we have, or when we need to produce high strength concrete in that range, improving the ITZ in those traditional methods will not be very effective. We have to look for other ways. Okay, so let's look really at the modulus of elasticity. The elastic characteristics generally of a material are a measure of its stiffness, as we have stated in the introduction. Concrete is a non-linear, inelastic material in both tension and compression. So the term modulus of elasticity must be applied with some caution here, since it does not represent a single value, as it does for a linear elastic material. Okay, as we have, this is what I will talk about this figure in a bit. Okay, so the term is adapted here to describe the response of the material at various points along the stress strain curve. Okay, so again, we need to apply this with some caution, because it does not represent one single value, like, for example, modulus elasticity of steel in tension. It's not. So in spite of the nonlinear behavior of concrete, an estimate of the elastic modulus, which is basically the ratio between the applied stress and instantaneous strain within an assumed proportional limit, is still necessary, basically for determining the stresses induced by strains associated with environmental effects, like drying, shrinkage, thermal effects, and also needed, for computing the design stresses under load in simple elements and moments and deflections and complicated structures. So we still need it, although it is a very definite term. Okay. So the closest really approximation to a modulus of elasticity derived from a truly elastic response is the initial tangent modulus. Look at it here, which is the slope of the tangent at the curve of the curve at the origin. As you can see here, the slope of this curve at the origin. This is the stress strain curve under compression of concrete. All right, so this modulus is not used in the design of concrete structures, since it applies only to small stresses and strains. Okay, so it is likely that the dynamic modulus of elasticity, which is determined from the fundamental frequency of vibration of a specimen, which we will discuss later actually, may be a reasonable estimate of this, of the initial tangent modulus, since its determination involves only very small displacements of the material. Okay, so that is the limitation of this initial tangent modulus. A more practical measure of the modulus of elasticity is the secant modulus. Let's go back. Okay, this is the secant modulus. Okay. This is, equal to the slope of the secant between the origin and a point on the stress strain curve. The second, modulus, this secant modulus includes an element of non-linearity, and clearly its value depends on the value of the level of the applied stress chosen. Okay, and again, another limitation. You see, it is, again, we said the slope between the origin and a point here, all right? So the secant modulus is, as we said, often used in design since it simplifies the calculation of the section properties. The use of the secant modulus has, little effect up to the typical working stresses, since, the deviation from linear behavior is relatively minor within the stress range, okay? The initial tangent modulus or the secant modulus are not really always easily determined because of errors in the measurement, due to specimen seating at the initiation of the test, or due to the existence of pre-existing, cracks that close up under applied load. In such a case, the chord modulus, which is determined according to ASTM C469, is used, which is basically the slope of a linear line drawn between 2 points on the stress strain curve. Let's go back here. This is the chord modulus right here, okay, drawn between 2 points on the stress strain curve. Let's go back to the slide. Okay, so the initial tangent modulus, basically or typically corresponds to the slope of the curve at 50 microstrains. This strain is used as, the lower limit of the chord modulus, to avoid any error in the initial portion of the stress strain curve. The chord modulus and the secant modulus, are determined at 40% of the compressive strength, 40% of the compressive strength, and will not be very different, okay? So remember that. So although the chord modulus, will be more precise in this case, okay? So let me repeat. As we said, the initial tangent modulus typically corresponds to the slope of the curve at 50 macrostrains, okay? The second, the second point, at 0.4 of the ultimate stress, okay? And as I said, this strain is used as the lower limit for the chord modulus, which is the 50 macrostrains, to avoid any error in the initial portion of the stress strain curve. The chord modulus and the secant modulus determined, at 40% of the compressive strength, will not be very different. Remember that, all right? But, and as I said, the chord will be more precise. The chord modulus is more conservative measure than the initial tangent modulus and is more easily determined experimentally. On the other hand, though, the chord modulus will underestimate the additional strain that occurs when stress in excess of 40% of the compressive strength, is imposed on the concrete. Okay, so this is a limitation. In such case, though, the tangent modulus measured at the point of interest is better measure of the concrete response, to relatively small additional stresses. And again, there are many limitations. I know there are a lot of information to digest here, but keep up with me. Okay, so in order, to study the response as a composite material, okay, describing the modulus of elasticity of concrete as a function of the properties of its constituent materials provides a tool to really better understand the nature of the response of the material to stress. The composite models are often used to determine the relative importance of these components in determining the overall behavior of the concrete. All right? So to gain really basic understanding, concrete is often modeled as two-phase material with aggregates particles embedded in a matrix of cement paste, or as a three-phase material in which the third phase, represents the interfacial transition zone we talked about before. For the purposes of these models, the aggregates and the paste phases are normally considered to be homogeneous and isotropic, the materials themselves. So experience has shown that models of this type can provide very good approximation of the mechanical behavior of concrete if the properties of the components are known. Okay, so that's we need to do our homework first. So to fully really describe a system with one or more dispersed phases or particles embedded in a continuous matrix, it is necessary to consider the shape, size, distribution, concentration, orientation, the spatial distribution, the composition of these, of the dispersed phase, the composition of the continuous phase, and the properties of the interfacial region between these continuous and dispersed phases. That's very important to know all what we need to know about these materials in order to really be able to model them and get some meaningful results, okay? So, basically, simply describing the geometry of a system such as concrete, in terms of the parameters is difficult. So it is helpful to consider two extreme cases of phase arrangements. The parallel model or the void model and the series, which is the reuse model, as shown here in this figures, A and B, okay? The blank haze is representing the paste matrix, and the hatched area represents the aggregates, okay? The parallel system, though, just to make sure we understand, in which the two phases are subject to uniform strain. So basically they are subject to the same strain. This provides the upper bound solution for the elastic parameter of interest. The series model, which is this model, in which phases are subject to uniform stress. These elements here all subject to the same stress. It provides the lower bound solution, okay? This is the upper bound solution because we have here uniform strain in all in both phases, okay? So if we look, using these two models I just talked about, to calculate the modulus of elasticity, the results in the equations shown for each model, as you can see here. Okay, so basically this is for the parallel or uniform strain model, and this is for the series or the uniform stress model, okay? So basically, just to define these terms here, the E sub P and E sub A, those represent the moduli of elasticity. This is of concrete, this is E sub C, this is modulus of elasticity of the composite, which is the concrete in this case. E sub P is that of the paste, and E sub A is that, modulus of the aggregate, okay? And the V sub P, V sub A, this is V sub P is the volume fraction of the paste, and this is the volume fraction of the aggregates, okay? And the same basically here. So these are the equations. This is the equation in the parallel model. This is the equation in the series model. So, however, though, neither of these two models of course, is quite correct. Since the components of concrete are subjected to neither uniform stress nor uniform strain under load because of the highly heterogeneous nature of concrete, as we mentioned, and the localized stresses and strains are quite different from the nominal applied stresses and strains. Okay, so that's something to keep in mind. These are models, are approximation, and variations could occur. Okay, so speaking of the localized stresses and strain, in this figure here, shown here on this slide, this is based on studies using photoelastic coatings on the surface of concrete specimen and compression. Okay, the localized strains, we were able to measure the localized stresses and strain due to this technique, so just keep it at that. As we can see the results from this technique, the localized strains may be as much as 4.5 times the average strains, as you can see here. Look at this value, look at this value. This is the average right here, and this is some of the localized strains were measured. Okay, and the localized stresses may be, more than twice as high. Look at this is the average, and this is some of the localized areas, what we get, between 2000 or like 1700 or 170 to 340 or 200 to 400, okay? So the largest strains, occur at the contact zone between the paste and aggregate, which is accounting for the early formation of the bond microcracks. Okay, so you keep that in mind. Okay, so as we said, both the series and the uniform models have their limitations and shortcomings. We have one model suggested by Hirsch, which is obtained by combining the moduli obtained from the parallel and series models, presented just now. The Hirsch model, is illustrated in this figure right here, as you can see. Okay, and expressed, as you can see in this equation right here. Okay, so basically where, x and 1 minus x are the relative proportions of the material conforming to the upper and lower bound solutions, respectively. Okay, for many concretes, x is approximately 0.5. All right. So one limitation, both the series and the Hirsch models, is that, for the case of when the elastic E sub A actually equals to 0, they predict the concrete modulus of elasticity to be 0, which is not true. Okay, so that's the case. As you can see here, if we define the terms, actually where they were defined, all these terms were defined before, and we said, these x and the 1 minus x are the relative proportions of the material conforming to the upper and lower bound solutions, as we said. But we said, there is one limitation. When x is equal 0, the model reduces to basically series model, and for perfect bond, x equals 1 becomes the parallel model. But as I said, for many concretes, x is approximately 0.5. Okay. So, and again, due to this, that every model now presents some challenges. So there's still another model, as shown in this figure, which is the counter model, and which is basically expressed in this equation. Okay, and where AC basically A sub E sub C is the modulus of elasticity of concrete, E sub P and A for paste and aggregates respectively, and these are the volume portions. Okay, so this is another model proposed by Conto. Okay, so, and again, these models, like I said, every model presents some challenges, but you know, it also it adds value to the modeling of the concrete as a composite materials. Okay, so besides those models, you know, we have, you know, even more sophisticated representations of the two-phase materials. You know, this is provided by the Haitian-Strickman, or abbreviated as H-S bounds. Let's keep it at that, HS bounds, okay? As shown in this table right here though. The HS bounds are expressed in terms of the bulk moduli, which is K, and the G, and the shear, which is the shear moduli of the component materials, okay? So the relationship between E, which is the elastic modulus of the concrete, G, the shear, and K is the bulk, and Poisson's ratio, which is denoted by the Greek symbol nu, are also, you know, given in the table, as you can see here, okay? The studies have shown that, you know, the moduli of elasticity calculated using the Haitian-Strickman bounds, as well as, you know, the values of the modulus of elasticity of concrete, you know, calculated the Hirsch and Conto models, provide good representations for many, but not all concretes. And again, this, as I said, it has to be used with caution, as I said at the beginning. It requires knowledge and it requires experience, mostly knowledge of the properties of the materials and these mathematical models, in order to be able to draw some conclusions. I mean, for the purpose of this class, I am presenting this material as basically for the sake of knowledge, and as basically a reference for you to understand what really has gone on to develop these relationships for the modulus of elasticity. But for the sake of the practical engineering problems we deal with, there is a practical determination that I will present later. This is for you to know the science and the premise behind the development of these values, okay? Okay, so again, talking about these models, you know, graphically, a comparison of all models is shown on the figure I'm going to show on the next slide. You know, as shown, like the Hirsch and the Conto models, the Haitian-Strickman bounds lie between the upper and lower bounds, you know, obtained with the parallel and series models. Okay, so this graph here shows the relation between the modulus of elasticity of concrete and the volume fraction of aggregate, you know, for the structural models, okay? X is equals to 0.5, you know, for the Hirsch model, and the Poisson's ratio of 0.2 for the Haitian-Strickman bounds, okay? So as I just mentioned a little bit ago, you know, studies have shown that, you know, moduli of elasticity calculated using the Haitian-Strickman bounds, as well as the values of the modulus of elasticity of concrete calculated using the Hirsch and Conto models, provide good representations for many, but not for all concretes. The differences between the measured values of the modulus of elasticity of concrete and the values predicted using these models, you know, especially the ones, you know, measured below the lower Haitian-Strickman bounds, have been interpreted as being due to the presence of the interfacial transition zone, which, as I said before, acts as a third phase. Okay, so the two models can be used to calculate the elastic moduli of three-phase composites, as shown here in the table on this slide here. Okay, so the simpler of these two, which is the logarithmic mixture rule, requires knowledge of the modulus of elasticity, E sub I, and V sub I, which are basically the modulus of elasticity and the volume fraction of the ITZ. Okay. The more sophisticated model, which is the Haitian bounds, requires knowledge of the values we introduced just earlier, the K sub I, G sub I, which are the bulk and shear moduli of the interfacial transition zone. Okay, and also T sub R, which is, the ratio of the thickness of the ITZ to the equivalent radius of basically the assumed spherical inclusions, which represents the aggregate particles. Okay, as you can see, these are more sophisticated, mathematical, complicated mathematical models to calculate the modulus of elasticity of concrete as a three-phase model. Okay, as I said, these, I'm just presenting these for you guys, as a reference on the science behind what went on to determine the modulus of elasticity of concrete. Okay, so based on the measurements of the dynamic modulus of elasticity, which we will discuss later, and an analysis using the logarithmic mixture rule, the ratio of the E sub I values and to E sub P, which is the elastic modulus of the interfacial zone, to that of the paste, has been found to lie between 0.15 and 0.74, depending on the assumed thickness of the interfacial zone. For similar concrete, containing, listen to this about the role of silica fume. For similar concrete containing silica fume, the ratios lie between 0.5 to 0.88. This, which demonstrate greater density of the ITZ when silica fume is used in concrete. The same study found that the ratio of the shear modulus of the interfacial zone to that of the paste lie between 0.09 and 0.65 for concrete, without silica fume, and about 0.3 to 0.81 for concrete with silica fume. Other, studies have indicated that the ratios of the elastic modulus of the interfacial zone ratio to the elastic modulus of the paste maybe lie between 0.5 to 0.7. Okay, so that's really what I have presented, what I'm going to present about these models, and I said this is just for reference only. So let's move on now to the practical predictions of the model, the things that you could appreciate for use in the design of the concrete. For the material moduli calculated using the expressions, based on the models discussed previously are, principally to gain, as I said, better understanding of the behavior of concrete as a material. For structural design, the modulus of elasticity must be estimated based on readily available information, okay, such as concrete strength and density, values that you could appreciate and feel. Okay, so based on large number of tests run using, the procedures described, I will describe in later lectures about empirical, relationships between these properties and the modulus of elasticities have been established, as you can see here. Equation number 1, or I refer to it 1A because of the different units. This is, for in SI units, which is the modulus of elasticity of concrete can be determined from this relationship here. And for foot-pound units, or inch-pound units can be determined from this equation 1b. Okay, so all you need is the weight of the unit weight of the concrete and the F prime C, which is the compressive strength of the concrete. Okay. So where, as I said, E sub C is actually the secant modulus of elasticity, which is at about 45% of the ultimate strength. And W sub C, which is the unit weight of concrete in kilogram per cubic meter or pound per cubic foot. And F prime C is the compressive strength of the standard 150 by 300 millimeter or 6 by 12 inch cylinder in MPa or PSI, as whatever units you are using. Of course, assuming a density of our normal weight concrete is about, let's say, 2,320 kilogram per cubic meter or 145 pounds per cubic foot. These equations I presented earlier here will reduce to these expressions. The modulus of elasticity of concrete in SI units equals to 4,030 multiplied by the square root of F prime C. This is in GPa, and or 57,000 multiplied by the square root of F prime C. This is in pound or PSI units. Okay, so these, as I said, the practical determination of the modulus of elasticity from values that you are familiar with and values or information that are readily available and that can be appreciated and understood more easily. Okay, so this is basically the essence, and these are the values used, determined according to, as I said, ACI, the ACI building code, ACI 318. All right, okay, I went too fast. Let me go back. Okay, so one more, before I finish this lecture, one more term I'm going to talk about, which is the Poisson's ratio, or the simple nu in Greek letters. This is, this value is not often, required for the design, but can be determined conveniently by direct strain measurements in uniaxial compression, according to ASTM C469, or can be determined dynamically using, certain formula, which we will see later. So the Poisson's ratio for saturated concrete lies between, or in the range of 0.2 to 0.3, but it averages about 0.18, upon drying. So this change is not completely reversible in resaturation. Keep that in mind. For different concretes, Poisson's ratio generally falls in the range of 0.15 to 0.2. But the variation, as a function of concrete properties is not known precisely. Okay, so when determined, dynamically, the value is somewhat higher, averaging about 0.24, and this is properly more representative of elastic behavior. Okay, so this is what I'm going to mention about the Poisson's ratio, and later we might come across it again, but that's what you need to know about it now. Okay, I'm going to stop this lecture here. I know this lecture has been, going on for a while and it is too long. I just wanted to present all the information in continuously in one lecture, so it is more appreciated. Anyway, I will stop here, as I said, and next time we will start discussing the factors that affects the value of the modulus of elasticity of concrete. Okay, until then, thank you for watching, and I will see you next time. Thanks.